Hello, welcome back to Astrobeat. Today we're going to go over the concept of moments, center of gravity, turning effects, law of conservation of moments, or the principle of moments, and yeah, we'll do some quick lecture notes first, and then we'll move on to past paper questions. Hoping to cover this section within about 30 minutes. Okay, let's see. So let's do a quick recap. In our not last, but second last class, we saw that forces are capable of doing a number of actions. What's a force? It's a push or a pull in simplest words. And a force can move an object. If an object is already moving, it can slow it down. It can change the direction of an object. It can deform an object. And today, we're going to see that forces can cause objects to rotate as well. Okay? We'll see the condition for that in just a minute. Before that, think about a door. Okay? So if you push the door, you're applying force, it causes the door to rotate and it opens, right? So that rotation is a consequence of the force that you're applying. Okay? Now, the door rotates about the hinge, right? This point of rotation, or the point where the rotation happens, is called pivot. Okay? Now, in our syllabus, we're going to see two types of rotation. You can rotate clockwise or anti-clockwise. Clockwise is like this, and anti-clockwise is opposite to that. I think of it just how a clock, like the needle of the clock rotates. That's literally where the word clockwise comes from. So you can think about that. And now let's move on to some formal terminologies and what causes this rotation. So if you have a surface like a table and you have not a table, let's say you have a ruler, okay, and you place it on your hand and you're trying to balance that ruler on your hand. So what do you do if you're trying to do that? So let's forget about this example for now. Oops. Let's have a thinner pen. So I'll forget about my box for now. Move it here and I'll just move this as well. Okay. So let's say you have a ruler and you're trying to balance it on your hand or your finger. What you'll essentially do is put your hand in the very middle of the ruler at the 50 centimeters mark if it's a 1 meter ruler, and the ruler balances. But if you move your hand a little to the right or a little to the left, let's say if you move your hand here, then the ruler will rotate in this direction and it will fall down, right? Because there is more mass of the ruler on this side as compared to the right side, which causes this side to rotate anti-clockwise, right? Okay, so to balance something about a pivot point, you have to make sure that the rotation on both of the sides is equal. And what's that rotation? The term for that rotation is moment or torque. Okay? Now, if you place a box on this side of the ruler, now let's move past our example of the ruler. Let's say you have a little triangular object placed on the table and you place I don't mind a ruler actually. So let's say you place a ruler on that triangular box that's triangular object that's on the table. And if you place a box on the left side, it will cause the ruler to rotate in this direction. The reason is that the box has some weight. What's weight? Weight is a vector quantity or it's a force, right? So there is a force acting down and it's perpendicular to the pivot. So remember, whenever you have a force, that's perpendicular to the pivot, you will have rotation or moment. So what's moment? It's rotation about a pivot point when you have a force acting perpendicular to the line of sight of the pivot. So the pivot is like this, okay? And you have your force acting perpendicular to it, and you see rotation. And rotation will always be towards the pivot, like this. Okay, so if you have an arrow down, you bring it towards the pivot to see that it's anti-clockwise, because initially when I saw these arrows, I was like, okay, sorry, I might be confusing you. If not, I'm glad. So if you have another box here, that box also has some weight acting down. So let's call it W prime, just to differentiate between the two forces. I'll make it a little bigger. There we go. Okay, so if you have another box on the right side, it also has weight, which is the force acting down, and you might think, that they're both arrows acting down. How do I know which one's clockwise and which one's anti-clockwise? The answer is that you're going to bring this force towards the pivot to see the clockwise or anti-clockwise thing. Okay? So if you bring this arrow towards the pivot, this is anti-clockwise. And if you bring this one towards the pivot, you would see that this is clockwise. Okay? Now if I manually apply a force, let's say I don't have these boxes, or maybe let's leave one box on and remove the other box. And this box is applying a force down, but I manually apply a force up. So I manually apply a force up. In that case, this force is, what is it? What do you guys think? Is it clockwise or anti-clockwise? Oh, sorry, I already drew it, but if you have an arrow up, you're going to bring it towards the pivot like that, and this is anti-clockwise. And this one's also anti-clockwise, so this is just going to make the rotation faster. Okay? The takeaway from this diagram is that pivot is the point of rotation, and you have forces acting perpendicular to it. That's when rotation happens. Now, let's see what's moment. Moment is just the rotation or turning effect of a force about a pivot, and it's the product. If you want to look at the formula, this is the formula. It's the product of the force and the distance from the pivot, and the distance has to be perpendicular to the force, okay? Because here, if you notice, this is your force, this is your force, and you're going to multiply that with the distance between the force and the pivot, okay? And these two are perpendicular. So moment or rotation is a product of that force and the perpendicular distance from the force to the pivot. Okay? Wonderful. Now, why does it matter? Because we also saw a similar formula F cross D for work done. In that case, the distance was parallel. Let's recap that one. If you have a box and you apply a force on it, the box will travel some distance in the direction of the force, right? Very simple. And you see that this force and this distance, they're parallel. So we have a formula for work done, which is force multiplied by the distance traveled in the direction of the force. So F and D are parallel here. In the case of rotation or moment, F and D are perpendicular. Okay? Now what's the unit for moment? It's just Newton meters, because force has the unit newtons, distance has the unit meters, so you multiply the units and you get the units of Newton meters for moments. Okay, now this is, I wrote magic tool here because I don't know the name of this tool. I'm just really bad with remembering names of things, and I'm sure this is very common, don't come after me. This is probably, I'm not going to say anything just to not make myself look like a fool here, but this is a very constant, no, not constant, sorry, very common tool. I'll call it a screw tightener for now. And you would notice that to tighten a screw, we apply a force down, like we rotate it, we apply a force down, and this screw rotates or it's tightened, right? So how is the screw tightened? It's tightened because it rotates, right? So this is your pivot point, and you apply a force down, and your distance and force are perpendicular. This is another example demonstrating how how in a rotation or in moments the force and distance are perpendicular. Okay. Now let's look at the relationship between moment, force, and distance. Remember that we can almost, like not almost, but most of the times we can look at the relationship between two quantities just from their formula. Okay? So the condition here is that if you have three quantities in a formula or more than three, in order to determine the relationship between two quantities, you have to keep the third one constant. Okay? So if I want to look at the relationship between force and moment, I will have to put the distance constant. Okay? So if you have the same distance same distance from the pivot to the force, then the more the force, the more the rotation. Okay? So the idea is that moment and force are directly proportional. And if you keep the force constant and you look at the relationship between moment and distance, then they're also directly proportional. I think we should start calling moment rotation because that might just intuitively be more stimulating. So I'll just say rotation for moment for just a few minutes at least for the lecture. Okay, let's look at an example to understand this relationship. We'll go back to our door example. You might have noticed that the doorknob is farthest from the pivot point or the hinge. Why is the doorknob farthest from the hinge and not right next to it or in the middle or at the top or at the bottom? I mean, top bottom makes sense. It's hard to reach and uncomfortable. But at the same height, why is it not here? Why is the doorknob to the farthest? The answer is that for the same amount of force, okay, for the same amount of force, the more distance there is between the pivot and the force, the more rotation you will get, the higher the moment, okay? So if you're applying the force, you're applying the force inwards, right? And it's really hard to see it on a 2D diagram, but you can think about it right when you open a door, or you might want to open a door right now if that's helpful. And you would notice that the force that you're applying inwards is perpendicular to the pivot. So that's one thing. The second thing is that the doorknob being very far from the hinge or the pivot causes a higher rotation. So we establish a concept that for the same force, rotation is proportional to distance. The more distance there is between the pivot and the force that you're applying, the more rotation you'll get, or the higher the moment. All good? Perfect. Next, we have the principle of moments. It says that if clockwise moment is equal to anti-clockwise moment, then the body is in equilibrium. Now, what's equilibrium? Equilibrium means that something stays as it is, like it's not changing. There's no change in the state of an object. Okay? It could be stationary. If something's stationary, it's in equilibrium because it's not changing what it's doing, right? And if something's moving at a constant speed, not speed, sorry, in a constant velocity, that thing is also in equilibrium because it's just going on about itself and it's not altering its pathway or changing anything about it. So whenever something is doing what it's doing and there's no external factors affecting what it's doing or how it's existing, we say that that object is in equilibrium. Okay? Yeah, all good. So we understand what equilibrium is. there are two conditions for equilibrium. The first condition that I believe we did discuss it in section of forces, but if not, here we are. So the first condition for equilibrium is that the net force on an object has to be zero. So the first condition is that the net force is zero. What does that mean? It means that there's nothing causing the object to move, because from Newton's second law, F equals ma, we know that if net force is zero, then one of the two quantities from your product m or a must be zero. Of course, if an object is existing, its mass can't be zero. It has to be the acceleration, which is zero, and we get net force zero. So if net force is zero, your acceleration is zero, and we know that the formula for acceleration is rate of change of velocity. If acceleration is zero, that means your change in velocity is zero. Because of course, if you have zero here, and the only way you can get zero is if you divide zero by any number. Because of course, time's going on, time won't be zero. The numerator, change in velocity, has to be zero. So we learn that when net force is zero, your acceleration is zero, therefore your change in velocity is zero. That means velocity is constant. So it's not that an object must, it's not, okay? It's not that an object has to be stationary in order to be equilibrium and in order for the net force to be zero. The net force can be zero even when the object is moving, but the condition is that its velocity must be constant, because in that case, acceleration will be zero and net force will ultimately be zero. I hope that's clear. And the second condition for equilibrium is that your clockwise moment is equal to the anti-clockwise moment. Okay? That just means that if you have an object 1 and an object 2 here, and they're both applying some force downwards, which is their weight, then the moment in this direction has to be equal to the moment in this direction. That way, the beam will still be balanced. Beam will be balanced even if their forces are different. And how can we do that? We can do that by changing distance of these objects from the pivot point. Because at the end of the day, we don't care about the force only, we care about the whole rotation that each object is causing, and we can change that rotation by changing the distance of these objects from the pivot. Because rotation depends on both force and distance. Okay? So this rule, clockwise moment equals anti-clockwise moment, can be written in a formulaic form. You can call the first object 1, or you can call 1 and this one 2. So you have F1d1 equals F2d2. Okay? I do have an example here which I want to discuss, but I'm not sure because we have past papers as well. It's okay. Let's look at this example. I will simplify it first here. Let me get rid of this third rotation for now. Okay, so the question in your exam will look something like this. So they'll tell you that the object is in equilibrium. So they'll establish this point, and then they'll give you the situation that you have the first object placed 0.3 meters away from the pivot, and the second object weighs 300 newtons. How far is it from the pivot to be in equilibrium? Okay? Now, this condition that the object is equilibrium is your indicator that you need to apply the principle of moments. And the principle of moments is that clockwise moment equals anti-clockwise moment. Okay? Now, clockwise, which one's clockwise? So if this one's going like this and this one's going like this one is clockwise. So clockwise is F2 d2 equals anti-clockwise. Anti-clockwise is this one. You apply the formula for moment, which is Fd, right? But you take the second and second here. Now what's the, oh, sorry, 1. It's 1, sorry. 1, 1. Now what's F2? F2 is 300 multiplied by, what's D2? This is D2, and we don't know it, so I'm just going to write D2. This is what we're finding. Then F1 is 700 multiplied by D1, which is 0.3 meters. So I'll just take 300 to that side. If it's multiplying here, it goes to the other side and it's divided. So D2 equals 700 over 300 multiplied by, I can write this decimal as a fraction, 3 over 10. And how do we do that? You should know this by now, but you can do it just by putting this sign in place of the decimal, put 1, and however many however many digits you have after this decimal, you have to put that many zeros. So the 0.3 becomes 3 over 10. Okay, so you can cut some zeros, 3 one times, and then cut another 0, and D2 is equals to 7 over 10, and you can write 0.7 meters. Looks simple, right? Let's do another example. I'll take this complex one now. Okay. Now this complex one introduces another mass, which is this one, the pink one, and the pink one has some distance from the pivot as well. And let's say the orange one is placed at, a bit closer, I'll do it this way. Let's say this one is placed at, let's say the orange distance is, where's my orange pen? Here. Let's say this one is 0.5 meters. And you want to find out this distance for the third one. Again, we're going to do the same thing. The question will be that the system is in equilibrium and you have to find the 3, okay? We're going to apply a principle of moment as soon as we see equilibrium. We're going to run to principle of moments, which is clockwise moment equals anti-clockwise moment. Oops. Yeah, it's recording. Okay, so now you have to identify which of these 3 is or are clockwise and which one's anti-clockwise. How do we do that? Take your arrow towards the pivot. What about the first one? Is it clockwise or anti-clockwise? This is anti-clockwise. So the first one, let's label it, oops, anti-clockwise. Let's look at the second one. The second one is on the right side of the pivot, so you have to take it towards the pivot, and you go like this. Is it clockwise or anti-clockwise? Of course, it's clockwise. And the second one is also clockwise. So 2 and 3 are clockwise, so I'm just going to apply the formula of moment on both 2 and 3. So I'll have F2 D2 plus F3 D3 equals F1 D1. Okay, so if you have more than one rotation in the clockwise side, we're going to add the individual momenta, of those 2 objects. F2, I would like you to pause it and do it yourself, and then match your answer working with mine. So F2 is 300 multiplied by, I'm using a dot to represent multiplication, multiplied by 0.5, or let me just use brackets to not cause any confusion, 0.5 plus F3 is 150 multiplied by D3, that's what we're finding, equals F1 700 multiplied by D1, which is 0.3. Okay, so half of 300, 150 plus 150 D2 equals 700 into 3 over 10, zeros cancel. So you have 150 D2 here equals 7 3 times 21, so that's 210. Take away 150. So I'm just bringing this 150 to that side and subtracting it. So that would be 150 d2 equals 210 take away 150 would be 110 take away 50, 60. And then d2 equals 60 over 150, zeros cancel, and 3 2 times, 3 5 times, so you have 2 over 5, 2.4, so 0.4 meters. Whoa, diagram is very off. It's okay. So the D3, oh, why am I, oh, this is 3, 3, 3, 3. So D3 is 0.4 meters. If you do this placement, you'll get the object to be in equilibrium. Amazing. Let's do, I hope this idea of principle of moments is clear because this is the most tested uh, concept from this chapter. Next, we have the idea of center of gravity. Center of gravity is just the point at which the weight of an object may be considered to act. Look at this wording. It's very clever, considered. Now, if you have ever tried to balance a ruler on your finger, you would notice that if you place your hand right in the very middle, the ruler is balanced, right? Now, it's not that the entire weight of the ruler is in the middle, but somehow you balance it by putting your hand in the very middle. The reason is that the entire weight can be considered to be acting at that point. So if you have this ruler and you place your hand here, okay, let me just draw a hand, or like a finger here, toe, oops. I was trying to draw a nail as well. So a nail, okay. Now, you balance it. So your hand is providing an upwards force, and it can be balanced only if the downward force is balanced by the upward force. So the mass or the weight of the ruler is distributed throughout the length of the ruler, but you place your hand only at one point. So we can say, or we can consider the whole mass of the ruler to be acting at one point. And that point is called the center of mass or center of gravity of the object. Okay, so you should learn this definition, and I hope it makes sense. If it doesn't, feel free to ask me in the chat box or whenever is possible. I'll also drop my email address somewhere for you to write to me if there's any questions. Okay, yeah, so center of gravity is the point at which the weight of an object may be considered to act. How do we find center of gravity for objects? For symmetric objects, we'll just draw lines from the, like if it's an object with corners, you can draw lines from the vertices or corners of the object, and where all of the lines intersect, that's your center of mass. So you do the same for all of these three shapes. For a circle, you don't have any corners, so you can just draw lines from any side or corner, not a corner, but like any part of the circle. And where these lines intersect, that's your center of mass or center of gravity. We use these both the terms. They're pretty much pretty much okay, or it's okay to call them the same thing at your level of IGCSEs. Okay, now let's look at the idea of stability. Now that you know what center of gravity is, you can learn about stability. Okay, how to determine stability of an object. Now, what's stability? So if you have a water bottle on your table, try to push it a little bit, like a little bit. You will see that it comes back to its position. It moves a little, one of its sides is raised a little bit from the table, but it comes back to the table, right? So it's stable. But if you apply a bigger force, then it's more likely to topple over and not come back to being upright. Okay, That's because the center of mass of the water bottle has gone past its baseline. So this is the base of the bottle, and we call it the baseline, okay? And if you apply a little push, this and you draw a straight line down, as long as this line falls within the baseline, that thing is going to be stable. And if you apply a bigger force, you will again uh, draw a straight line down, but when it goes outside the baseline, it will topple over. Okay, so this concept tells us that the wider the base, the more stable something is. Okay, if I have a bottle with a bigger base, then its baseline is bigger. If I apply the same amount of force that I applied on the little bottle, you will see that the force causes the object to move the same. Okay, so you would see that both of them, they're overlapping. That surely means that the force caused the motion to be the same, but still the center of gravity of the bigger bottle lies within the baseline of the object, so it will come back to its original position. But even with this bigger force, this center of gravity lies within the baseline, so the object will be stable and it won't fall down. And remember that when the center of gravity is exactly on this corner, then it will stay in that position. Okay? It won't come back, it won't topple over, it will just be stabilized in that very position. You might or might not have seen people stacking crazy stuff on top of one another in weird angles. That's how they're doing. They are skilled enough to um, like put things in position such that the center of gravity doesn't go past the baseline. Okay, so we learn that the wider the base, the more stable an object. Okay? Okay, for asymmetrical objects, center of gravity is closer to the part where more mass is concentrated. So if you have a wider mouth of a flask, the center of gravity will be closer to that part. If the base is wider, then center of gravity will be towards the closer to the base. So lower the center of gravity. Oh yeah. Okay. So first thing, center of gravity is closer to uh, the part where more mass is concentrated. And the second point is that the lower center of gravity, the more stable the object. I mean, it's pretty clear if you were to apply a force or push both of these two objects, which one is likely to be more stable? The second one. The first one is more likely to fall down. So we learn that the lower the center of gravity of an object, the more stable it is. Uh, okay. Our last concept is investigating center of gravity. I don't think we'll be able to do any questions, unfortunately, today because I'm out of time, but let's cover this and we'll do questions tomorrow, inshallah. Okay, so investigating center of gravity. If you have an irregular object, you can't draw these lines randomly and say that center of gravity is in the middle. That's not what we do because, of course, it's irregular and you have different or varying distribution of mass all along the lamina. So we call this thin paper-like object or cloth a lamina. So we take a lamina and we poke very little holes on the corners, not corners, but the closer to the edges of the lamina. Okay, and we poke little holes because we don't want the lamina to lose its mass in case we make bigger holes because uh, the bigger the hole that you're making in the lamina, the more mass of the lamina you're removing. Okay? Or you're deforming it essentially. So we don't want that. Firstly. Secondly, what you're gonna do is that you're going to hang the lamina on a wall maybe. Like you're gonna poke a little pin in that hole and you will let it settle. So imagine if you have a paper and you poke a pencil in that little hole, then the paper will rotate a little bit and then it will settle down in one position. So let's say it settles in this form. What you'll do is you will draw a straight line from that hole down, okay? Basically, we take a plumb line, this thing. What it is that it's a thread with a stone at the bottom, just to make it straight, and then you draw a line on the paper. I'll repeat that. Might be confusing a little bit, but I'll repeat it before the next lecture as well. I know I might be rushing it at this point, so I'm sorry about that. Okay, so we poke 3 holes. We let the paper or lamina hang from this one hole and we wait for it to settle. When it settles, we draw a straight line from this point 1 down, okay? And then we do the same thing for the other holes. We do the same thing for the second hole and we're going to do the same thing for the third hole. We poke a hole, we put a pin in the second hole, we let it rotate as much as it wants, and then we make it settle down. Once it settles, we draw a line down like that. We do the same thing for the third one. We wait for it to settle and then we draw a line. And the point where the 3 lines intersect, that is the center of gravity of that irregular object. Okay? So that was it for this one. Let's do a quick recap. A force is capable of causing an object to rotate, and when the applied force is perpendicular to the pivot, then we have rotation, okay? And we can find the amount of that rotation or moment by multiplying that force with the distance between the force and the pivot point, or the perpendicular distance. And the more the force, the more the rotation, the larger the distance between the pivot and the force, the more the rotation. Principle of moments says that clockwise moment is equal to anti-clockwise moment when an object is in equilibrium. And the second condition is that net force is 0. So when you're working on problems and you see the word equilibrium and you have to find out the moment or the distance or any one quantity in the problem, the first step is to apply the principle of moments, which is that clockwise moment is equals to anti-clockwise moment. Your next step is to identify which one's clockwise and which one's anti-clockwise. And if there's more than one clockwise or anti-clockwise moments, you're going to add them on separate sides of the equation. So since we have 2 clockwise moments, we added the 2 individual clockwise momenta and we equated that to the anti-clockwise moment. And we just algebraically solve it to get our final answer. If my computation anywhere happens to be inaccurate, please feel free to correct me. I'm not really good at computations. Next, center of gravity is the point where the entire weight of an object appears to be acting, and if you apply a counter force on that center of gravity point, you can balance the object. Stability is the idea of how stable something is. Yeah, so if you apply a force and the center of gravity of an object falls within the baseline of the object, it is going to come back to its stable position, which is the original one, right on the ground or the table, upright. But if the force causes the center of gravity to fall outside of the baseline, the object will topple over. And the wider the base of an object, the more stable it is. The lower the center of gravity of an object, the more stable it is. That is also why F1 cars or sports cars are so low, because they're trying to lower their center of gravity so that when they take sharp turns, they don't topple over or they don't crash and can smoothly, go over curved roads without any accidents. And you can find the center of gravity of an irregular object by this method, where you poke little holes, you hang it, wait for it to stabilize and come to an equilibrium position, and then you draw a straight line down. You do that for two to three different positions, and where all of these lines intersect, that's your center of gravity. Okay, that is it for today, and I'll see you tomorrow. Take care.